Good morning, everyone. So today's the day, exam tonight. We'll be walking around and checking rooms, but the same location as exam 1. And we will again be grading them, posting solutions for you over the weekend. You get them back next week in lab. Homework 8 did go up this morning. It's there. It's on Anova. You covered Anova in class this week. In labs, we covered it in our notes. So you can try any question out. Maybe tomorrow, maybe sometime this weekend to take a look at that. Due next Thursday. There'll be a homework on regression, homework 9, and there'll be one homework on chi-squared, which will probably be a bit shorter since I don't have quite a full week to give it to you. But I want you to try one of each type of chi-squared problem, so maybe 3 questions, so you get that practice too. Because we do not have that many more lectures. It's already going to be April tomorrow. Wait, today's Thursday what? March 31st. All right, questions or comments from you first? Anything at all that you want to ask at the beginning? Otherwise, we do have a little new, and we'll turn to finishing our review together for the later half. Question or comment at all now? Yes? What is power of the test? Power is a probability. I had someone email me last night that said, power of the test is the probability of a type 2 error. No, it's related to the probability of a type 2 error by its complement. Power of the test is something you want to be high. Power of the test is the complement of how likely it is to make a type 2 error. Now what is a type 2 error again? That's where you stay with H naught, but HA was really true. And the complement of that event, HA is still true, and you end up rejecting H naught, going with HA when HA is true. That's a good thing. And the chance of doing that is the power of the test. Power is the probability that you correctly reject H naught because HA is really true. And there's different factors that influence the power, which you fairly well know, I hope. Larger sample size makes sense. If you have a larger sample size, you should be more likely to detect what is the truth. If HA is really true, then the chance of choosing that power of the test should go up. Another factor that influences power is what? Alpha. Now alpha is probability calculated on the other curve under H naught being true. But once you pick that cut, moving that cut changes alpha and changes beta in opposite directions. Does that help a little? So it is a chance of correctly making the decision you want to make as a researcher, selecting HA, rejecting H naught when HA is true. It is the probability of that. Good. Was there another one? Yeah.
Can you explain the QQ plots and what they say about normality?
QQ plots. You use that to do what? Check for normality of what? Of your population model. That your model and your population is normally distributed. But you're doing that, check. Hey guys, I'm doing this for everyone's benefit, so if you don't mind listening, even if you maybe already know what a QQ plot is, that'd be great. QQ plot, though, is still made with your data. But you're not checking that your sample is normally distributed. You're checking that your sample looks like it came from a population that is normally distributed. And so what does your QQ plot do? It plots your data on one axis. It's ordered in terms of percentiles against sort of the values of z that you would have expected to see if it were a normal model. So it'll take the 10th percentile of your data set and plot it against the 10th percentile of a standard normal. And it'll do that for the 20th and the 30th and all the other percentiles in your data. And of course, if the percentiles are matching up with your data to a normal curve, then the fit is pretty good. And they should fall along a straight line with a fairly straight line positive slope. Now your points may not fall exactly on a straight line, but they should not have any pattern fluctuating around that line. So you're plotting the data which came from your population to see if you can assume the model for your population of responses is normal. How many QQ plots would you have to make If you're doing a one sample t-test, one of your response. How many QQ plots would you have to make if you're doing a two independent sample t-test? Two, one of each set of data. How many for the paired t-test? One. You make it of your differences, because that's what you're having assumptions about. You're not assuming the befores have a normal model or the afters, but the differences do. Good. In Anova, you have to make a QQ plot for each of your population, samples from your populations. Go ahead. When you're doing differences, paired data, all you're really focusing on are the differences and not the befores and afters separately. One QQ plot of the differences. Okay? All right. One more? Otherwise, we'll turn to new, but still come back to review. Yeah?
If you're looking up p-values based on test statistics and it falls in between two, on the exam, are you allowed to list in between these two like we did in lecture?
Yes. If I don't have output given to you, so you could find the p-value exactly, then you might have to find bounds for it, because sometimes it falls in between on that t-table. If it's a z test you're doing, just take carry your z out to two places after the decimal, because that's what your z table goes up to. You can look up a z statistic of 2.45, even though your test statistic was 2.4998 or something like that. But on a t-table, you likely will fall in between or off the edge on one side or the other, and therefore you'll have to give me some bounds instead. But if the output's there and you're doing a t-test, what does SPSS always give you? Gives you the two-sided p-value for your t-test, assuming you took the t you got and the opposite one and did the two tails. That may not be your p-value. If you quickly think through or sketch your picture of what the p-value really is with your test statistic you got and the direction you're supposed to go, then you'll know what to do with that two-sided p-value and find the right one. You do have to cut it in half, but do you have to do that other step of 1 minus or not? Good. All right, we're going to do very little new material today, and then we'll turn back to doing our final review questions, and I've got a few tangents off of those too. All right. The topic we have started this week, just the descriptive side, is regression. Looking at the relationship between two quantitative variables. I think page 1, is it 188 that we finished? Went through that page where we talked about the correlation. This is the data set that we've been analyzing for the last few pages on predicting a final exam score from the exam 2 score. We came up with what we call the least squares regression line. Now, you're going to see before we finish this newest stuff today that you can get that line from the output by just pulling off the two numbers. That calculation table is what the computer's doing for you. If you've got the line, you can make some predictions. That's what we did last time. We plugged in a few values of x, got some predicted values out, and then saw for the students in the data set, we were off in some respect. What were those distances again? Those vertical distances of the points to the line, those are called residuals. Your observed errors. There are 6 of them if you have 6 points in your data set. And they are something that will relate to whether or not we have a significant linear relationship next week. We'll be using that error quantity. We ended with the other descriptor, the idea of using this thing called R, the correlation, to measure how strong the linear relationship is. We drew a few pictures. We talked about what kind of values R could take on. The correlation for our particular data set turns out to be, and we'll be calculating it in just a moment, turns out to be 0.889, which I hope makes sense with the picture anyway, that it is positive, that it is fairly strong, because the closer to plus or minus 1 is stronger. We have a fairly positive, strong linear relationship here. So let's see where we're going to get this value of R, not with the formula that's on the bottom of that page 188, but rather from this concept called R squared, which is described on the next page, page 189. So R was always between -1 and +1. So R squared is always between always between 0 and 1. If you square the negatives, they become the positives. What are other things that are always between 0 and 1? Probabilities, p-values, proportions, right? I don't want to see any p-value tonight that's 2.8 or 372 or anything like that. Remember we talked about how you can gain some points if you're running late on getting through the work and you have a p-value that needs to be there so you can make a decision or write out a conclusion. What can you do? Put down a p-value and then make the decision and conclusion for that p-value. Even though the p-value is wrong -1, the other 3 points or 4 points, you could still get to show me you know how to use a p-value to make a decision and write up a conclusion. All right, R squared is also like a proportion. It's going to be a proportion of total variability that our linear model explains. Helps us to predict. So here's our scatter plot again. And if you look at just the final exam scores, they varied quite a bit, didn't they? All the way from down here, we had final exam scores in the 50s all the way up to the 90s. So the overall variability in just the response is quite a bit. So this overall spread or variability is the overall variability in the response in Y. If I didn't have the information about the exam 2, if I just had to predict the next person's final exam score, and all I had was the 6 final exam scores from my sample, I would probably use the average final exam score from my sample. And the average final exam score from the sample was a 75. 75 happens to be the Y bar that we got when we averaged those 6 observations. So if I didn't have information on this explanatory variable, this x, and I had to still predict the response, the final exam score for the next person, I'd probably pick 75, just because that's what the average of these 6 students got. But can you see that the variability around that line is going to be quite a bit? And that's what this total variability is trying to capture here. If you use just the information only in your response, you still got quite a bit of variability. You'll be off in your predictions quite a lot. We can do better. We can do better because we have this information on the x-axis here, this exam 2 score information. And we could fit a line that relates these 2 variables together. And if we do fit that line and relate them together, well, then we're going to have fewer errors when we use that line to make predictions. So we have our best fitting line. Now the errors are not quite as much. That total variability there that's left over still after you fit the line is much smaller. I was able to do better. I started with a lot of variability. I fit the line and use x instead, and I'm still left with some variability, but it's not as much. I've been able to explain a lot of that variability away. So these residuals end up being what is the sort of variation that is not accounted for by our linear regression. Still left over. So I started out with a lot of variability in my response. I use this explanatory variable, and I still have some variability left in those predictions when I use that line, but I certainly have gone from a lot to a little. I've explained a lot away. And R squared is going to measure what proportion have you explained. And I hope that's a high proportion. R squared is going to take the total sums of squares, which was the summation just from the Y bar. We calculated that in our calculation table on Tuesday. R squared says take that total sums of squares, the total variability, subtract off the sums of squares for error, and make that as a fraction of the total. Started out with this total amount, you're still left over with that error amount, and what's the difference between those two on the top is called the sums of squares due to the model. So I can quantify how much variability I had to start with in my response. I can quantify how much variability is still left if I fit the line and use it. That's sums of squares for error. The difference between those is what my model has explained, and I'll take that as a fraction of the total. And that measure R squared is a very nice measure of saying, is this a good fitting model? I want to use the x and pick the right explanatory that will make R squared high, very large. In fact, some programs let you put in a whole bunch of x's that you want to consider, It fits all the different models and finds the one that gives you the highest R squared. So you can pick the best fitting model. Here is your definition, or actually more of an interpretation. R squared represents that proportion of that total variability in final exam scores that we're going to be able to explain by this linear relationship with exam 2. Now, it won't be perfect, +1, unless all the points lined up exactly on the straight line. It is related to R's. If R is close to -1 or +1, R squared is close to +1 for a large proportion. All right, so let's take the total and error sums of squares that we have already calculated from our couple of calculation tables a few pages back. We found this 1300 back on that first calculation table, I think page 186. And then we found the error sums of squares when we looked at all those residuals from that second table, and that was 272. And our line is the one that makes that error sums of squares as small as possible. So what's left over and explained by the model? The 1300 is what we started with. We're still left with 272. So the part that we've explained by our fitting of this linear model is over 1,000 out of the 1,300. And that is our R squared, 0.791. Not quite 80%. So we have that about 79%, 79.1% of the variation in our response. Which one's our response again? The final exam scores. About 79% of the variability we saw in the final exam scores can be accounted for by the linear relationship it has with the exam 2 scores. So if you have R squared, or can get it from the calculations you already have done, then we can get R from it rather than that other longer formula. You have to remember that you might take the minus instead of the plus. You have to put the right sign in front because the correlation could be negative or positive. R squared is always positive. The sign matches your slope, but in this case we want the positive square root of 0.791, and that's where we will get the 889. A fairly strong positive correlation leads to a model that has a nice high R squared, saying the model fits very well. There's still, though, what percent of the variability that's left over that I haven't explained? About 20, 21%. And that 20 or 21% that's left over might be able to be explained by other factors, if I could think of other things that I could put into the model and add. You know, homework scores, or how much time you've been studying, or whatever it might be that could also affect the final exam score, and I might have even a higher R squared model, better fitting model. All right. This quantity is a nice summary. It's one of the standard ones that comes out. There is a couple pages in your text that have some good examples. I don't know if those are the right pages. I think they changed, but I'll update that on my notes and put them up for you. But the comments that are here are important. You have to look at the scatter plot to make sure you have a linear relationship. If it's not linear, you can't do this least squares linear modeling that we're doing here. There are other regression models. You can take courses upon courses on just regression techniques for polynomial fitting, log linear, logit, different kinds of regression modeling. So anything you want to try to model, there's a model out there that could be fit for it. We talked a little bit about outliers a couple different times. Okay, does an outlier affect a mean or a median more? A mean, right? The outliers can pull a mean in one direction or the other. And when we calculated our slope, B1, and that B0 the other day, they were with means, x bars and y bars, and standard deviations get involved there. So any outlier we see in a scatter plot here could have quite a lot of influence on the regression results. You can have a scatter plot that basically looks pretty well linear with a positive slope, and you get one outlier, and that can drastically pull the line towards it and make it look like it doesn't fit anything then. So some outliers have much more influence than others. Look at your scatter plot first. It's always a good advice. And then there's this thing called extrapolation. Predicting outside the range of your data. Very easy to do. You can take a model that describes a child's height based on their age. They do that when you take your child in and they measure how tall and they put them on that model, show what percentile they're at and so on. You take that model that works very well for, say, 6 to 12-year-olds, and you put in someone who's 25 years old and you get them to be like over 8 feet tall because you don't grow the same. The model that's linear for the younger years doesn't continue on out. So if you took a model for some range of x's and you start plugging in other x's way outside that range, that's called extrapolating. And it can lead to risky predictions and ones that are not accurate. So that's where you get a question, like on an exam, that says, should you use your model to predict the income for someone whose job number of years of experience is this value, and that value is outside the range of where you modeled. If we say should you need to kind of ask, well, should I? Is it in the range? Is it reasonable to make that prediction or not? And then I've got one other picture to draw here. It has to do with idea that sometimes we start gathering data and combine groups together when we really need to look at them separately. Let's suppose we're looking at number of TV hours watched by your child. How many hours of TV do you let your child watch on a weekday? And Y is the reading level of that child. And this is for, say, elementary school children. And so data is gathered on studying these elementary school children, and we get points that look something like this. Which would be a fairly strong, positive, linear relationship saying that I should let my child watch more TV because it's going to lead them to have higher reading levels. Right or wrong? There's two things wrong with that. One, just because there's a correlation between two things doesn't mean that one caused the other. Very easy to have reports that are written up in the news lead you to think that this is the cause of that. If you change this value, you will make that change. It might not be the causing factor. There might be a correlation. You can take a lot of variables, plot them, and there'll be a correlation between them. You can take number of divorces and banana exports for countries and plot them and get a correlation, but one does not apply the other at all. So that's one caution, that we don't write things that are too strong in our conclusions, and we don't say this has proven this relationship. You keep saying that correlation over and over in multiple studies across multiple backgrounds and regions and so on, and that starts to build the evidence of there being a link, but it's not necessarily based on one study. And then the other issue is that when we looked at the data a little bit more, turned out that these couple kids right here were the kindergartners, and these right here were maybe the first graders, and there's a few second graders in the study, all the way up to, say, fifth graders here at the end. And if you looked at the results by grade level, by age, there isn't much of a correlation there. In fact, in some places it's a little bit negative instead. By combining the groups across these subgroups, I've led to inappropriate conclusions. What we have here is a third variable that has a name. It's mixed up with the reading level because age also affects reading level. And also your age will allow you to watch more TV perhaps when you're older versus younger. So age or grade would be a confounding variable. If we included age or grade level in the regression model, then we would be able to parse out what's still left due to the number of TV hours, and that probably would not have a significant effect. All right, and one last page, which is to take a glimpse at what you will see in your pre-lab and labs next week. Oh, there's my comic. Happy? Non-linear, but it makes me happy. Okay. You will definitely see output on the final exam from regression, because I don't need you to do all those calculations by hand at all. What you see on the next page there is your typical basic output in any regression problem when you simply ask it to do a linear regression. Just going to quickly step through a couple of the highlights, and my last clicker question regarding something towards the bottom. Be another couple minutes yet, but it'll be a question you could actually be asked tonight, so we'll make it relevant. So the different pieces of this output. The first piece that comes out by default, it tells you what your model consists of. Notice it's got a nice footer right here. It tells you what one is the dependent variable, and it tells you which variables were put into your model. Which ones were the x? Which variables were entered into the model to help be an explanatory variable, and which one is your dependent variable. And notice there are options here. You have different regression things you can do in SPSS. You can have more than one variable come in. You can have variables be removed because you might have it set up to do some method. Here are all the possible variables. Do a stepwise method. Put one in, put the next one in if it helps with R squared. Makes it bigger or not. Kind of stepwise through and find the optimal fitting model. This one I don't always have on the output because it'll be clear by the description or background of the problem which is x and which is y. The next one, though, should have some numbers in there that look familiar. It's called the model summary. And there's this thing called R. There's an R squared sitting next to it, too. The R that's here does match with R's that we found just a minute ago, the 889. But one thing we have to note here is that SPSS gives us there the absolute value of R. It's actually called this big capital R, which is the multiple regression coefficient, rather than the simple linear regression correlation. And so when you don't have many x's in the model, then this thing does become your single little r, but it only is with the absolute value, because capital R for multiple regression can only be positive. So we do have to remember that you might have to put a sign in front of it if your slope was negative. Then you might have to say it's negative 0.889, but ours is positive here. You also have the R squared. So right there you have that 79% of the variability in the final exams can be accounted for by those scores on exam 2 and that linear relationship. The adjusted R squared we're not going to worry about too much now in this class. You will use that quite a bit if you took another class where you do have many x's used to explain the response. Because sometimes if you start putting in a lot of x's, you get a really good fitting model, but it's kind of overfit, and it looks inflated in that R squared. What I mean by that is if you only had one x in the model, and to explain one y, and your equation is going to be that linear model, so there's two parameters in there, slope and intercept. Well, what if I only have 2 points? You think you could fit a linear model to that pretty well? Right. And your R squared would be +1. Your R would be perfect. So when the number of data points is too close to how many parameters you're fitting in the model, how many x's you have, you can get a really good fitting model that's not really appropriate. So you have to have the adjustment that your sample size needs to be large enough and not too close to how many parameters you're fitting. And that's what the adjusted R squared does for you. But we're going to have data, more than just 6 in regular problems, and only 2 coefficients that we're estimating. So we usually don't have a problem, and those two numbers are fairly consistent. Now this last guy here, this standard error of the estimated regression line, will be a very helpful one next week when we do the inference. This is going to be called the S for the regression line. Remember how you interpret a standard deviation? It's roughly how far away those things, whatever they are from the true mean on average. Well, that's going to give you an amount of how far away will my predictions be from those actual values. How far off are the points from the line? So we'll use that to give or take around some best estimates to make some confidence intervals. The Anova section, we don't have too much to look at there now, except we did find quite a few of these guys. Those are those sums of squares. There's the 1300, the sums of squares for total. You found that in that first calculation table. There's the sums of squares due to the residuals or error. And then the model one is right there too, which we found by subtraction. So if you only had the Anova part of the output, could you get the R squared from these values here? Well, that's how we defined R squared. It's defined on your yellow card as the model or regression model sums of squares, that 1027 over the 1300. So if the model summary wasn't provided, but this part of the output was provided, you do have that ability to still get your R squared and your R from those. We will be using this F statistic next week and doing a formal test with that p-value sitting next to it. But the bottom, last part of the output is the most important part in the sense that it gives you your equation of the line. Those values right there are your coefficients, your b's. There's your intercept term, 121.667, and your slope, the B0 and the B1. Take a look at what the row headers say. The first row says constant, or intercept term. It doesn't have anything multiplied by it. It's just the 21.667. The second line in that model listing is your x, your explanatory variable. What sits next to the x? The slope, your B1. And then there's quite a bit more regarding the intercept and slope. What's right next to them? Couple of standard errors. How do you form a confidence interval in general? Best estimate plus or minus a few standard errors. So we'll use those standard errors, which have some atrocious formulas behind them. They're on your yellow card, but you'll calculate them right there. But we'll use that to make an interval estimate for what the true slope might be, using our best guess of 1.046. You see another quantity further down. Doesn't this look familiar? What is that in this model? That was your correlation. And there it'll be with the right sign. If the slope was positive, that correlation will be positive. If the slope was negative, that value there will be the negative correlation, correctly written. Then there'll be a couple of t-statistics and a couple of p-values sitting next to them. And those p-values are probably what kind of p-values? One-sided or two-sided? They're two-sided. Some of the output in SPSS writes two-sided in there. For some reason, this regression stuff doesn't. I asked them, why don't you just put two-sided there too? To let us know that. But they always give you a two-sided p-value for their t-tests. All right, so my one-clicker question has to do with this one important p-value that you will use more next week, but you know how to use a p-value. We'll use clickers for this question. We'll use them for the first of our review questions together, and then we'll be able to put them away. But that p-value, 0.018. Once you have a p-value, you know how to use it to make a decision. With our one-clicker question and 0.018, oops, it's working. Stop. All right, polling. It asks you, for which of these significance levels would you be statistically significant? At which of those levels? You've got the p-value. I'm having you pick the alpha. The alpha at which you would be statistically significant at. All right, there are some answers coming in, and they are not all consistent. A lot of you are picking B, and that would be a correct choice. Also, those who are picking C, it is a correct choice, but not A. And yes, you can tell. You're asking for which levels of alpha would you be statistically significant at? What does it mean to be statistically significant? Your p-value is what? Less than or? Which alphas could go here if your p-value is 0.018? I need something that's bigger or equal to 0.018. B, or C. You would not be significant at a 1%, but you would at a 5 or 10% or anything larger than 0.018. Is that okay? Usually the alpha is set up front, and then you compare your p-value to it. If you know alpha and you know you were significant, you can tell me what the p-value must have been about. Something less than or equal to that alpha. All right, time for review. We're doing the last 3 questions, 4, 5, and 6. We'll do those paired or independent with clickers. Many of you maybe have tried the questions already. That's great. If you haven't, I'd like you to pull that out and look at them for just a moment or two. I'm going to give you about 3 or 4 minutes to check your answers with your neighbor on 4, 5, or 6. I've got a couple copies, maybe about 4, if you don't have your sheet with you. That's about all I've got left. Yep, 4. Who needs one? You're welcome. The first 4. Anyone else? Yeah. Anyone else need one? There you go. Still like to give you a couple more minutes. Try out the questions first if you haven't, or check with your neighbor. All right, let's take a look. We're doing number 4, paired or independent. So in each of these two scenarios, or background, there's two sets of numbers. In this first scenario, there are some highway gas mileages being recorded and some city driving gas mileages being recorded. Now, in some of those old exams, you've seen variations of this, where it could have been one out of those different 5 parameters. And sometimes we ask you, does the researcher want to do a confidence interval here, or are they looking to do a hypothesis test? Now here we tell you we're going to create a confidence interval. But the very first line talks about you want to estimate the difference in the highway versus city average gas mileage. You want to estimate. That means confidence interval. Because a confidence interval is an interval of reasonable values. It's an interval estimate rather than a point estimate. My point estimate would be my best guess, whether that's d bar or mu or x bar 1 minus x bar 2, but I go out from that each way and give you an interval estimate instead. So you've got 8 cars, you've got highway and city gas mileage measured, so there'll be a highway mileages recorded here, and city mileage is also recorded. There are 2 sets of numbers, and a very high % of you would get it right if this were an exam question, which is good. It's paired. You might be asked, how do you know it's paired? What are these first 2 measurements paired or matched by? The car. They were 2 measurements made on the same cars. 8 cars, the same car by the same driver was driven on the highway, record that mileage, and also on the city driving course. So there is something that goes together between those 2 that's not shared with the others. You could think of the third column variable, and it's car, the 8 different cars, because they might be different types of cars. And they go together then. Good. So what would be the parameter that you would be making a confidence interval for? What would be the parameter that you would be making this confidence interval for with this data? Is the parameter mu d or d bar? The parameter that you would use your data to estimate is mu d. What you would calculate on your data is d bar. I would have to do what with this data set? I'd have to make another column and make that the differences. I would use those 8 differences to get the d bar, to get the s sub d. Now, unless the numbers are really nice and the d bar turns out to be a whole number, so that calculating even the standard deviation here would be really pretty easy, most of the time you're given the summaries. Now, in some questions, you might be given the summaries for the highway and the city, those means and standard deviations, along with the differences. And if it were an independent design, the differences wouldn't even make sense to use. But here they would be, and I would use that d bar and the s on those differences. Paired data. Good. So now the other one that's there, is it independent or paired? Let's see if I can get things started here. Hold on a minute, but there we go. Do you think if there's 2 true, false, there's always one that's true and one that's false? Not necessarily. I like to put things in 3s so that reading through the description, we're measuring how long they had to stay in the hospital. Pediatric asthma patients. Comparing 2 insurance companies, because your insurance sometimes dictates how long you end up staying. Now, most of you are, again, doing very well. It is the other case. It's independent. There are 2 separate samples of 300. You have insurer A length of stays and those patients that were under the other insurance, what their lengths of stays were. There were 300 here and another 300 here just to have a nice balanced design. But why would you compare that length of stay for that one pediatrics patient under that insurance with that one there? They're all pediatric lengths of stays for asthma cases, but they have that in common across all of them. When it's in independent samples, you're comparing this group as a whole to this group as a whole, not one-to-one. The parameter here would be what? mu1 minus mu2. Would I be doing a test about that or make a confidence interval estimate? I want to see if the average length for A is significantly different for the average length for B. I want to assess if there is a significant difference. Now, you could actually do it with a confidence interval, couldn't you? Because it's a two-sided test. But when you hear the word test, assess, is this one larger than the other one? You're asking a question, how they compare, not just let's estimate how they're different or not, but a test. So this would be a hypothesis test here. All right, now there was a really good exam question, old exam question, and I've had a couple of you come up and ask about it, so I said I would do it and talk through it. If you were doing an independent samples test here, it would be a t-test. What would you still have to decide between? What was it? Pooled and unpooled, right? If I have the data and the summary, you're going to have both t-tests there for the pooled and the unpooled method. So you would have to look at some things in the data to help you decide. What would be some things you could look at? The two S's, S1 and S2, are they similar? You don't have to say they are equal. No, they probably won't be equal, but they're similar. How about, what's the other nice test that's sitting there sometimes from the output? Levene's, which is usually done at a 10% level to help you decide whether pooling is reasonable or not. It's really testing if the variances in your populations are equal or not equal. And then another thing that you could look at are side-by-side box plots, and that's what that homework or old exam question was about. It had a couple of side-by-side box plots. In one data set, it had box plots that were just about the same for treatment 1 and treatment 2. In the other set of data, it had box plots that were not exactly the same. Now, in both cases, though, what aspects tells you that you could probably do a pooled test if you wanted to? IQRs are quite similar. I drew them almost the same here. Even if they're off just a little bit, it's okay. I'm actually quite surprised at how off the box plots can look, and the Levene's test says it's still okay. And you have this one here, and same thing here. The overall ranges, the IQRs are pretty similar. So you'll be able to do a pooled test for either one of them. Now, the question, I believe, asked, for which data set would the p-value for testing if the means are equal be larger? For which data set would the p-value for testing whether the means were the same or not be larger? That's what it asked. So what was the H0 again? H0 is that the two means are the same. They are equal or their difference is 0. The alternative is that there's some difference, not equal. I want to know the p-value will be larger for which one? What does it mean if the p-value is large? That means you, what? You stay with H0. Which one is going to tell you to stay with H0? A. Because the medians are practically the same there. So the means are going to be very close. You'll probably not have any evidence here to reject H0, but you might have some here. P-value smaller for that test, p-value larger. Both can have the test done, but I probably won't see a significant difference in that first data set. I might see some difference, whether it's significant or not, more so here. Okay? Good. Let's take a look at number 5. This kind of comes from a competition between Josh and Drake. It was Drake back in number 3. Who says that the mean service time for his customers is 15 minutes? That was supposed to be his established model, his true mean. Another restaurant owner studying service times for his customers to establish whether or not he can say that the average time for being served here is less than 15 minutes. He'd like to be able to promote that. So what do? They go and take 100 customers and measure their service times. So they're measuring how long it took them between when they placed the order and they got their food. How much time did that take? You're given right here that your two conditions are met to be able to do the test you want to do here. All right, we're measuring service time. That is quantitative. I want to establish if the mean service time is significantly less than 15 minutes. Mean, not proportion. What hypotheses do I want to be testing here? Population mean. The true mean service time for all of Josh's customers at lunchtime would be what? Equal to 15 versus less than. Could someone get full credit for doing greater than or equal to 15 in the numerator there, that H naught? Yeah. Are we less than 15 or are we not less than 15? The equal, though, is always in H naught. I have 100 service times. I have one sample randomly selected from my population. And you've got a short summary in part B of what the results were from that sample. It even says it right there. The sample mean was 14 minutes. Now, they didn't say the word sample. They said the 100 service times resulted in a mean of 14 minutes. You know that that is your sample mean, which is not mu, but x bar. And the standard error of the mean is 0.5 minutes. You're asked to compute the t, your test statistics. So from your formula card, it says you calculate the difference between your sample mean and that null value in standard error units. It writes it a couple ways. So what goes on top? Sample mean was 14. Comparing that to the null value of 15. 15 may not be the true mean, but it is the true mean under H naught. It's the null value. And what goes on the bottom? Some people would initially put 0.5 over the square root of 100. Common mistake. We didn't give you S, we gave you the S over square root of n, the standard error of the mean already calculated. 0.5. That's a nice summary to have. When you're reporting a sample mean, to have that standard error allows you to already kind of get that give or take, maybe a few of those standard errors to make a confidence interval very quickly. Most standard output gives you the S and the standard error right there. So this is what? A -2. Now what if you did this wrong on the exam? Maybe -2 points on the t statistic, but if you did your p-value and your decision, everything right, nothing else would be taken off from that. Okay, you've seen on old exams and such, what does that -2 mean? Interpret that -2 t statistic value for me in the context of this problem. Our sample mean was 2 standard errors below the hypothesized value of 15 minutes. 2 standard errors below because it was negative. Now your t of -2 happens to be one of those nice t statistic values that allows you to find the p-value exactly when you use your table A2. Could you come up with what S was in this data set? Would you have been able to solve for that? Because you have the square root of n, and you got the 0.5 total part, so you could solve. All right, p-value next. Now when I say show your work, sometimes your work is your sketch. If I ask you to make a nice complete sketch, then I'll want labels. But if you're just doing a quick sketch to show me what you're doing, that's enough. I'm doing a t-test, so I better draw the model for my t-statistic when H naught's true, which would be a t-distribution. How many degrees of freedom? 99. I don't have 99 degrees of freedom in my table, so I'm going to be a little conservative and use 90 instead. Now my table also doesn't have any negatives, and I got a -2. And what will my p-value be? The probability of getting what you did get for your test statistic, or something even more extreme. Which way is more extreme? To the left. Question?
So what on the exam should we write P99 or P9?
If you're finding the p-value, I need to kind of know which row you're using. Okay? If I ask you what is the model for your test statistic under H0, well, the actual true model is t with 99. But I don't have that information that I can use, so I'm going to approximate it with the t of 90. You can say using 90 degrees of freedom approximately. Since I need to kind of know which row. But does it make that much of a difference whether we use 90? None at all. So your answer will be the same. All right, so there's the picture of the p-value. There's no negatives on the top of the chart, but there are positive numbers, and you can pretend they're negatives when you're doing left side instead of the right side. Right? If you're looking at 2, and that number in the chart is giving you the area to the right of +2, that's the same thing as what I wanted. So what is this exact p-value? Out to 3 places after the decimal anyway, 0.024. Was there a question still?
No, why would we use T instead of Z in this example? Because isn't it big enough that CLT would...
Good question. CLT is going to help you here. That your model for your service times is, for the average service time is approximately normal, but we already had that without the CLT because we already had normality beginning. It is true that the S, which you could have solved for, was probably pretty close to the true sigma because it's based on 100 observations, but it's still not exact, perhaps. It is a t distribution. There is still some difference between a t distribution with 99 degrees of freedom and a true normal 0,1. That's why we have lots of different lines here for you to use. It's true when you get further down, you're almost at the z, but we're not there yet. Good. All right. So there's our p-value. That allows you to make your decision. What level of significance here? 5% level significance. Should be able to cross out 2 of them for sure, because what's your decision going to be? Rejecting H0 or failing to reject? We're rejecting, because our p-value is small, 0.024. And what does that mean? Look at your HA. It means that that sample mean of 14 that we got, it was significantly less than 15. We have evidence to say that the population mean service time is less than 15 because our sample mean service time was significantly 2 standard errors below 15, and that was significant. Good. And we have one last question. This one has to do with defective rates for 2 different machines. The word rate, or the incidence of some side effect, or the word proportion, tell you're talking about p's. Here's 2 machines, so it's a p1 and p2. And what you're given right here is the 90% confidence interval for the difference in the population rates or population proportions. There's a range of values for what we think the difference in population defective rates for our 2 machines might be at a 90% level of confidence. All right, we know we can use a confidence interval to do a test. It does give us an indication of what we might decide, especially if the test is two-sided. And our significance level and our confidence level match up in the sense of giving you back 100%. And that's what we've got here. 10% significance level, use your 90% confidence interval to decide. So which statement are we going to select here? What are you looking for in your interval? Is 0 there? Because I'm asking you to test formally, is P1 minus P2 0 or not? I want you to do that test using your confidence interval. Okay, is 0 possible? It's not in that interval. 0 is not a possible value. I'm not going to stay with H0. I am going to reject H0. What do you know if you're going to be rejecting H naught? That your p-value is small. How small? Well, it must be something less than or equal to 10%. It could be 0.08, it could be 0.07, 0.04, lots of possibilities. Would you be able to circle one of these? Or what would be the right thing to circle if I said do it at a 5% level? Would you be able to make that decision here? You know your p-value is less than 10% for sure. That's all you know, 10 or less. It could be 8, it could be 0.02, 8% point. I don't know how it compares to 0.05, so I can't make the decision. Your interval doesn't have 0 now, but what if you made a 95% confidence interval? That's going to be what? Wider. It might have 0 in there. Without knowing the sample sizes and the ability to redo that interval, I can't tell. And what about this last one? Just want a number to go there. I want to figure out what value will make this correct. The sample proportion of defectives for the first machine was what % higher than that for the second machine? What were the results of the data? What does this interval say right here? That's a range of reasonable values for the difference in the true proportions. I would estimate the first machine to have 1 to 3% higher defectives than machine 2. But in the actual sample, what was the actual difference in the sample proportions? I'm asking you to figure out, in some sense, what is P1 hat minus P2 hat? What did that turn out to be in our data? What's the midpoint of this interval? And the midpoint of every interval is your best guess at what the difference in the population values might be. 0.02 is that difference in sample rates. The first machine had 2% higher defectives as compared to machine number 2. And that's our review.